Recording, there we go. Uh, Today's a long class. We need to talk about surface integrals, which are kind of an upgrade of line integrals. And I've tried to pare down this class as much as possible, but still you'll see that we won't make it all the way through this. And so there'll certainly be a problem or two that I can post, depending on how much, I may actually make another little mini video or something like this. Because yeah, I mean, there's more problems even than this than I wanted to cover. And unfortunately that we just don't have time in 50 minutes, but we'll give it our best shot. So surface integrals, just like line integrals, need to be separated into two different flavors. The first flavor is a surface integral with a scalar function. So in the line integral days, this was adding up. Remember, we were pretending that we were a whale and eating up plankton, or we were summing up some density along a spring and stuff like this, right? This would be a couple of examples. So for surface integrals, same sort of deal. We can talk about with scalar functions first, and that's kind of what this video was about here. But maybe a little bit worse than for just line integrals, you have to separate them one more time into, is your surface given to you explicitly or parametrically? So we talked about in last Wednesday's class, which I hope that everyone has seen the video that posted for that by now. But if not, you have a little bit of makeup to do. We saw for surface area, right, that if you had an explicit surface, you're very interested in this quantity here, the square root of, some partial derivatives, things squared, added together, you add the one, all that sort of stuff. That's for an explicit surface. And then for a parametric surface, right, you had this magnitude of this cross product, this R sub S cross R sub T sort of business here. So now, if we make this equal to our ds in each one of these cases, then we can define surface area as just the integral of 1 ds, which is somewhat beautiful because we've seen that the integral of 1 is quite often this, very interesting metric, right? We've had the integral of 1 as a line integral showing that this is arc length. We've had the integral of 1 dA, which is area in the xy plane. We've had the triple integral of 1 dV, which is volume, right? And now we have the double integral of 1 over some surface, ds, right, as surface area. And with this parametrization, with this parameter, this capital S, right, then we can talk about adding up other quantities besides just area over a surface. So my silly example here that I do is snakes on a plane. So you have a snake density function, and you have some plane loaded up with these snakes. And the question is, how many snakes in total are on the plane? So we're adding up the snake density function across the surface of the plane, and we can calculate out how many snakes are on the plane. All right, so that was the pre-class video for scalar surface integrals. And then there was also a video, 2 videos before this class, about flux. So this is surface integrals with vector fields. And so we need to talk first about having oriented surfaces. So this is, similar to when we were talking about Green's theorem and stuff like this, a positive orientation, a negative orientation being counterclockwise or clockwise. Well, it's a little bit different when you talk about surfaces. But you need to be able to distinguish an inside from an outside. And it turns out that that's not always the case. You can't always do this for some surfaces out there. Now, luckily in our class, we're going to restrict ourselves to these nice surfaces. But for instance, for Mobius strips and Klein bottles and stuff like this, you can't actually define an inside from an outside. And so these are non-orientable surfaces. But however, the majority of the surfaces we've talked about, planes and spheres and quadric surfaces and stuff like this, right, we can define an inside and an outside, or an upside and a downside sort of deal. So this will be equivalent to choosing a normal vector. We've already gotten some practice with this in 16.4b, right, when we had to choose either this plus or minus sort of business. So there'll be a lot of this choosing plus or minus, which will be equivalent to choosing an orientation for the surface. And again, we have 2 different formulas for our surface integral. One of them, if you have a explicit surface, a z equals surface, and one of them if you have a parametrized surface. And then we did a small example related to calculating this flux for a particular surface, for a particular vector field, and a region. All right, so that's the pre-class stuff. Any questions about really any of this before we jump into our stuff for today? All right. Well then, let's go ahead and transition. Oh, I'll get to that later. Oops, that's still pre-class stuff. That's why that's there. Here we are. So I'd like to start off by computing the surface integral z squared ds, where S is this unit sphere. And we're going to do it in two different ways. We're going to first express this surface parametrically, and then we're going to express this surface explicitly and calculate it out that way. So again, the surface that we are over is this unit sphere. It's a sphere of radius 1 centered at the origin. Before we even get into this, I want to think about, right, what's a reasonable answer? So I have a surface integral. So that is, we're summing up points on a surface. So not the inside, mind you. This isn't a triple integral. So it's not like inside of this, surface here. It's like actually on the surface of the balloon, not the innards as well. So we have a bunch of points on this surface of our balloon sort of deal. And for these, we're taking the z coordinate, we're squaring that, and then we're summing those all up. So because we're taking a bunch of, right, if it wasn't, by the way, if this was just z ds, could anyone tell me right now, without doing any work, what the answer would be? Hand raise here. 0, right? Because half of the z values are positive on the top half of them are negative on the bottom half. And so when you add up all of these z values, because there's the symmetry, you would just get 0. So this would be a very quick question. Now we have z squared, right? So we're adding up a bunch of positives. And so we know that our answer at the end of the day is going to be positive. All right, so we need to do this by expressing our surface parametrically. Now, because we have this full sphere here, we know back from 16.6, when we kind of first brought this up, maybe a good parametrization for this, right? We would steal from spherical. So I'm thinking about like x equals rho, sine phi, cosine theta. I'm thinking about y is equal to rho, sine phi, sine theta. And then I'm thinking about z is equal to rho, cosine phi. This is what's on our formula sheet, right? This is how we can express the Cartesian x, y, z into spherical. Now, when we're parametrizing a surface, we only get two parameters. We get s's and t's, or we get u's and v's, typically, right? Those are the typical variables that we use. So, but I have three variables, right? I have a rho, I have a phi, and I have a theta. And this is the case, right? If we are on just any point in space and we're expressing that, with our spherical coordinates. However, we are not in any point in space. We are on the surface of the sphere. And on the surface of the sphere, if we go ahead and convert this, this is equivalent to saying that rho is fixed at 1, right? We are one step away from the origin. And so therefore, if I wanted to express my sphere parametrically, maybe with s's and t's, I'm going to use maybe 1 sine s cosine t. So notice I've swapped in everywhere I see my rho, I put my 1 because we're on the surface of the sphere. And I'm going to use s's and t's, and you can see that I've replaced my phi with s and my theta with t. Next up, we would have 1 sine s sine t, and then finally 1 cosine s. If you want to get the entire sphere and include each point once and only once, right, you allow your phis to range from 0 to pi. and you allow your thetas to range from 0 to 2 pi. Now in our case, of course, phi is s and theta is t. So I can start to do some things now that I have a parametrization. The first thing that I can do is everywhere I see a z, right? After all, that's what my function is here, z squared. I can replace that with cosine of s, or 1 cosine of s. So you can see z squared is going to be cosine of s quantity squared. The other thing that I can do is, right, I can swap in this ds. So I'm going to jump back to our pre-class notes here, maybe just this once. But again, notice that we are summing up a scalar function, right? That doesn't have coordinates or anything like this, right? It's not a vector field. It's just z squared. So we're in this first case, and we're in a situation, right, where we're going to be dealing with a parametrized surface. So you can see that we can swap in, instead of this ds, we're going to be using the magnitude of this cross product of stuff, and then we can have our ds dt. So again, this is one of the equivalent ways of writing ds. So ds, if you have an explicitly defined surface, you can use the first one. If you have a parametrically defined surface, you can use the second one. All right, let's jump back. So this is going to be the magnitude of our cross product of tangent vectors, ds dt. Once we've said in ordering, and I've just written ds dt for the time being, we can include our bounds, right? I'm thinking about trying to maximize my partial credit here, right? So ds, right, if I do s's first, s's range from 0 to pi in order to get the entire sphere, and thetas or t's range from 0 to 2 pi, right? So I could plug those things in. This bit right here takes a little bit of time. And so I'm not going to do it here in class. I invite you to do this on your own to double check me. But my claim is actually the result is guessable. So my claim here is that we would have, and I'll be kind of suggestive here, that this magnitude of our cross product of things is 1 times sine of s. If you were to calculate this all out, 1 times sine of s. Why do I say that that is guessable? Anyone see this, the pattern where this comes from? I believe in you. I'll drink coffee and wait. Ooh, we have someone raising their hand online. Oh, I think they put it down. Any guesses? Jacobian. Yeah? What Jacobian, though? So when you switch into spherical normally, you get rho squared sine phi, right? Here we are switching into spherical essentially, right? And we have, well, our rho is 1 squared 1, and instead of phi, we had s, right? And so that's why it's guessable here, that this is actually, yes, the Jacobian. There aren't any t's in the third spot of our vector. Okay, yes, so that kind of helps things cancel out a bit. But yeah, so that's why we're getting this, is because essentially we're switching into spherical here. So this is kind of taking the place of our Jacobian. And so yes, that's a good intuition here. And so we can swap this in now. Cosine squared phi sine phi ds dt. Notice that our, oh, sorry, I wrote phis accidentally. Stay consistent, use s's, good. So now we can evaluate this. Notice that there are no t's in our integrand. There are no variables in our bounds, right? So we can kind of split off and do our t integral first. The integral of 1 dt from 0 to 2 pi, right? Similar to what we used to do with our thetas. And then this is going to be the same thing as like an integral of u squared and negative du, right? So we're going to be using a small u substitution for our s's. So if I was to integrate that, we would have what? Negative u cubed over 3. Double check if you take the derivative, we get back to where we started. Let's go ahead and swap back in. Instead of our u, it's going to be cosine of s, and evaluate that from 0 to pi. So again, you can double check. If we take the derivative of this, we get back to where we started. So this is a correct antiderivative. And let's see here. So we have negative 1/3. And when I plug in pi in for cosine, that would be negative 1. And then I need to cube that. So negative 1 cubed is going to be negative 1. So this negative 1 times negative 1 will be positive 1. And then I need to subtract away this, well, negative 1/3. So that's going to be plus 1/3. And when I plug in 0 into cosine, cosine of 0 is 1. Cube that, I still get 1. So my answer at the end of the day is going to be 4 pi over 3. All right, so we did get a positive number. That's nice. That's reassuring sort of deal. We did need to skip kind of this part. Again, I invite you to double check my work and see that you really do get this 1 sine s out of there. But other than that, right, this is kind of somewhat reasonable. Any questions on this one before we do the same problem one more time? All right, so this time though, we're going to carefully rip the surface into 2 surfaces and expressing them explicitly. So as you know, with the sphere here, given by x squared plus y squared plus z squared equals 1, if you tried to solve this as a z equals, you would have z equals the positive square root of 1 minus x squared minus y squared, and you'd have z equals the negative square root of 1 minus x squared minus y squared. And this corresponds to the top half of your sphere and the bottom half of your sphere. And so if you evaluate out our surface integral on the top half and you evaluate it out on the bottom half, then you can add those 2 results together and you'll get the surface integral on the entire sphere. The advantage is that we get to use the z equals sort of form here. And we saw last time that usually this goes a bit quicker. All right, so I'm going to focus on this top half for a little while. And then we'll actually see that the bottom half comes very quickly once you know what the top half is. All right, so in this case, we are doing our integral of z squared. Well, right, we know a z equals function. So I'm going to go ahead and substitute in, everywhere I see a z, my 1 minus x squared minus y squared. And again, we're integrating z squared. Now, because we have a z equals function that we're evaluating, let's jump back one more time to our pre-class notes and stare at, right, when we evaluate out our surface integrals with this ds's, you could either use the parametrically defined ds, or if you have a z equals function, right, with some number of x's and y's, that you can go ahead and take derivatives of those, right, and square them and add them together, throw them under a square root, and right, and that can be your ds. So that's what we're going to be using in this case. So I need to pull off to the side maybe for a little while. And I want to take some partial derivatives, right? So here is our z equals function. That's my g function. If I take a partial derivative of that with respect to x, well, the 1/2 comes down. We reduce our power by 1. So instead of the 1/2 power, we get to the negative 1/2 power. And then if I multiply by the derivative of the inside, again, with respect to x, well, the derivative of 1 is 0. The derivative of negative x squared would be negative 2x. And the derivative of negative y squared is 0. Again, constant with respect to x. We could simplify this a little bit. And this is maybe as clean as I can make it look. So the 1/2 and the 2 cancel out a little bit. And all of this stuff, 1 minus x squared minus y squared raised to the negative 1/2, we'll notice there's two things going on here. It is raised to a 1/2 power, but it's also negative. So the negative pushes it into the denominator. The 1/2 is really a square root. If I take a partial derivative with respect to y, it maybe is not surprising that you have pretty much the exact same thing. There's a lot of symmetry going on here, except for when you take the derivative of the inside, you're going to have negative 2y. Still the 1/2 and the 2 will cancel. You'll still have a y on top, right? And the bottom will be as is. So instead of ds, right, I'm going to swap that in for the square root of g sub x squared. So that's negative x divided by all this stuff squared, g sub y squared plus 1 dA. And now at this point, we're doing a regular old double integral. That dA is the same dA as we used to do in chapter 15, which means that we are now in the xy plane. So instead of hovering above here on our surface, right, we have smushed this down into the xy plane. And this right here is my region R. So you have to be kind of careful. The actual surface, S, versus, once you evaluated out your ds, and notice that we just have all x's and y's at this point, now we've smushed down into the xy plane, and we have this region in the xy plane. So if I go ahead and I look at this head on, well, this was a sphere of radius 1, and so when you take a sphere of radius 1 and you smush it down into the xy plane, it's maybe not surprising that you have a circle of radius 1 in the xy plane. All right, well, hopefully this simplifies because this looks kind of nasty, right? So maybe the first thing here, when you square root a square, you can simplify that. So we're just going to have 1 minus x squared minus y squared. Here we can start simplifying, right? Negative x times negative x is going to be positive x squared. Again, when you square a square root, those nicely cancel. So I needed to square both the top and the bottom here. And as we saw last time, that sometimes, you know, getting a common denominator is worthwhile, right? It's a little bit better than just like a fun algebra thing to do. And so since these first two have this denominator of 1 minus x squared minus y squared, right, I'm going to convert my 1 here, my last one, and get a common denominator. And you can notice that we have a positive x squared and a negative x squared then, when we have that common denominator. And better yet, we have a positive y squared and a negative y squared. And so that's very nice as well. Really, at this point, or any time in the near future, right, because we are doing this double integral over a circle, we're going to be leaning hard towards evaluating this with polar, right? When we evaluate double integrals, we have 3 different ways that we can do them. We can do y first and then x. We can do x first and then y, or we could decide to convert to polar. Because we are integrating over a circle of radius 1, right, we're going to be leaning hard towards polar. So let's go ahead and maybe start to convert this a little bit. If you factor out that negative, you do have an x squared plus y squared there. We have 1 minus r squared. When I simplify my square root of stuff, right, the square root of 1 on top is going to be 1. The square root on bottom, well, notice the denominator, this common denominator that we got is this 1 minus r squared. Our dA, now that we've decided to convert into polar, is going to be r dr d theta. And we know that our r's are going to range from 0 to 1, and our thetas will range from 0 to 2 pi. Because again, the region that we're over, we're trying to describe the circle of radius 1 here. notice that we have this exact same quantity on top and on bottom, right? One's inside of a square root though. So there is a little bit of cancellation that's going to be happening here. It doesn't fully cancel, right? But you could write this if you really wanted to, right? As this is the square root of this squared. So you can kind of imagine one of those square roots canceling on bottom and one of them remains on top, right? One doesn't cancel. And so when you do your cancellation, you're just going to have one square root left on top that doesn't go away. This r right here really saves us, right? This Jacobian r dr d theta. I sometimes see people, especially going into the final exam where we have a lot to remember, right? If you don't include that r there, you have to use like trigonometric substitution. It's a very difficult integral, right? But with this r here, right, it's just a nice u substitution. And so don't forget about your Jacobian, or if things are very, very difficult, especially when it comes to like quiz or exam problems or something like this, double check and see if you've made a mistake. Now, again, look at our thetas. There's no thetas anywhere inside of our integrand, the function that we're integrating. There are no thetas in either of our bounds, and so we can kind of split this off and do our theta integral first. The integral of 1 d theta will be theta. Evaluate that from 0 to 2 pi. We just get 2 pi. This is going to be a small u substitution. So if our u is this 1 minus r squared sort of deal, then we're going to have our du is negative 2r. So this would be the same thing as negative 1/2 du. So when I integrate this, u to the 1/2 power, raise that up by 1. We're going to have u to the 3/2 power, multiplied by the reciprocal there. And of course, we can double check. We'll also substitute it into this line instead of u. We'll put back our 1 minus r squared. And again, we needed to evaluate that from 0 to 1. When I plug in 1 into this, 1 minus 1 squared will be 0. Raise that to any power. Minus a negative 1/3. And when I plug in 0 into this, we get 1 raised to the 3/2 power. And so we get 2 pi over 3. Now I thought on our last problem that we got 4 pi over 3. Why did I get a different answer? Yeah. I only did half, right? So I now need to argue about the bottom half, right? So we're 1/2 done. Notice that in our formula here, first of all, we were integrating z squared. So if there's a negative here or not, when we go and we square it, we get the exact same thing. Also notice that when you go and you take these derivatives, our g sub x and our g sub y, right, there would be extra negatives here. But again, when you go and you square these things, they become positive. So it doesn't actually matter in this case, right, if there are these extra negatives or not, because there's a lot of squaring going on here. And so because of that, I can tell you that the integral on the bottom half, so if I broke this up to a bottom half as well, is also 2 pi over 3. Because of the symmetry. So our total answer over the entire sphere is going to be 2 pi over 3 for the top half, 2 pi over 3 for the bottom half, and so our final answer, 4 pi over 3. So if you did want to employ such a trick, and usually I would say quiz and exam problems would not be, require you to do such a trick. But if you did decide that you wanted to be clever like this, right, I would include a sentence or so just to explain to the graders kind of what you're doing and that you know what you're talking about, right? You wouldn't want to certainly say, 2 pi over 3 and then say equals 4 pi over 3 and then circle that one, right? That's nonsense. You've now said 2 pi over 3 is equal to 4 pi over 3. That's not true, right? So how did you get 4 pi over 3, right? And so that's where the extra sentence or so becomes very useful, and it explains, okay, yes, this person knows what they're talking about. All right. Any questions on this one here? Yeah, in the middle. Yeah, so the question for everyone online and whatnot is, how do you know when to use a parametric version versus when to use an explicit version, right? So certainly if your equation is solve z equals, right? So it really comes down to your surface equation. If your surface equation is solve z equals already, you're going to be using explicit, almost certainly. If the surface equation is given to you parametrically, you pretty much are going to be using the parametric, right? This is kind of a borderline case where it's not z equals, right? And it's not, and by the way, solving z equals, we had this, like, it was the worst case scenario for us, right? Because when we solved for z equals, we had plus and minus the situation, right? So yeah, this is probably the worst case scenario, in which case, you can see that really either one could be used, right? That's usually not the best type of question to make a quiz or an exam question, because you really want to have everyone, more or less choose the same option. So I would say that this is probably unlikely to be, a quiz or exam style question. Does that make sense? So let me give you I'll answer your question as well by showing you the next question. So here's something that's maybe a little bit more typical, a little bit more reasonably done in a time setting. Evaluate out this surface integral. Again, you have a nice scalar function here. You don't have any coordinates or things like this, right? It's not a vector field. It's just the function is y, where S is the surface, z equals this stuff here, x's range between 0 and 1, and y's range between 0 and 2. So this is one of these that I want to make sure that I have time to talk about flux. And so I'll tell you right now, when I did this earlier, I got this answer here, 1/12 times 18 to the 3/2 minus 2 to the 3/2. So I invite you to try this problem on your own. And then this will be one of them that I include in my post-class video or notes or whatnot. Or if there's time, I'll happily come back to this. But I'm worried about not being able to say enough words about flux. And so I want to make sure that I dedicate some class time to this. But this one right here, because it's a z equals surface, you're going to be pretty much using your explicit equation. All right, good. Well, with that, let me switch gears a little bit. And I want to talk about surface integrals with vector fields, aka flux. And again, there are two different flavors of these types of problems. If your surface is given to you explicitly, or if your surface is given to you parametrically. So here's an example problem. This is the same flux, mind you, that we had in 16.4b when we first came up with flux. But now instead of flux across some curve, right, we're talking about the flux across the surface. So we have some interesting vector field. Notice now we don't have a scalar function, we have a vector field. We want to find the upward flux across the portion of the plane that lies inside of the cylinder. All right. So the first thing, right, upward flux. Flux is really a surface integral of your vector field dot, and now this is a bold ds. So it's not the same as the previous ds that we had. This is a bold s there. So it could have given you this as well and said to evaluate that, and it would have been the same problem. So first of all, I want you to notice the difference between the way that these flux integrals look versus what we were doing previously, right? Again, with a scalar function, you don't have coordinates. You have a regular old ds here, right? Not a bold ds or anything like this. It wouldn't make sense to say a dot product, right? Because you don't have vectors. All right, so these are the key differences. for when you should be using this flux equation versus when you're just doing a integral, a surface integral over some scalar function. All right, so this is what I want to evaluate out. And again, if I jump back to my pre-class notes, we're now not talking about these surface integrals with scalar functions. We're talking about these surface integrals with vector fields. And when it comes to this, really there were two different formulas that we have. One is if we have a z equals function, and one is if we have a parametrically defined function. In which case you can see that our ds, right, gets evaluated differently in either one of these cases. So, well, in this case, let's go back to our problem and take a quick look. We have, right, we're finding the upward flux across this portion of the plane. Now, the plane would normally go on forever, right? In which case we'd probably have like an infinite flux or something like this. But we don't want the plane to go on forever. We want only the piece that lies inside of the cylinder. And so our equation for our surface is this one right here. Let's draw a quick picture of this too. So we have our plane, some interesting slanted plane. This would normally go on forever, but we're only interested in the piece that lies inside of the cylinder, right? And so this plane is, cylinder would go on forever like this, free in the z direction. And there's going to be a piece of our plane that lies inside of this cylinder. This is what we're interested in calculating the flux of. And so because of this, right, there's kind of two surface equations that we need to be very careful about. One of them is describing your actual surface that you want to calculate the flux of, and one of them is telling you about a boundary. It's telling you that, hey, the surface doesn't go on forever. It's going to stop someplace. So in this case, our cylinder equation is the boundary. It's saying, well, don't let the plane go on forever, guys. Let's cut it off at a certain spot, right? The actual surface that we're interested in calculating the flux of is the plane, though, x plus y plus z equals 1. This is critically important because one of these is very easy to solve z equals, right? I can solve this plane z equals very fast. On the other hand, the cylinder, which is not the surface that we're interested in, it's just the boundary, right? There's no z to solve z equals, right? If this was our surface, we'd have to solve it parametrically because there's no way to solve this z equals. All right, so our surface equation is z equals 1 minus x minus y if we want to set this up explicitly, which usually that's a bit easier. So let's go ahead and start to evaluate some of this stuff. Because we're going to be swapping in, right, and solving this explicitly, instead of z here, I'm going to swap in and do 1 minus x minus y. Oops. Dot, and this bold ds, remember, has a normal vector. It's going to be plus and minus. Our normal vector, we get way back from like 14.4. We talked about this a little bit in the pre-class video, right? But it goes your g sub x, right? So your surface equation, take the partial derivative of that with respect to x, I get -1. Take the partial derivative of it with respect to y, I get -1. And then in your z coordinates, it's always just -1. Kind of annoying in this case that all of them happen to be -1. Let's go back and stare at this one more time in our pre-class video. Again, if you have a z equals function for your surface, that's your g. It could have any number of x's and y's. You take a partial derivative with respect to x for your first component, a partial derivative with respect to y for your second component, and your z component is always -1. It could be plus or minus that. And again, that plus and minus is going to come down to the orientation. All right. Well, in our case, we could think about this now. We could also think about it later. But this one's not so bad. So we'll think about it now. In this case, it says that we're interested in calculating out the upward flux. So when we're in 3 dimensions, x's, y's, and z's, right? Upward means that we have a positive z component. And so if I wanted to make sure that I was calculating out the upward flux and not the downward flux, right, I would look at my z component, and I want to make sure that that's a positive number. And so again, choosing this orientation is the same as choosing this plus and minus. And I'm going to go ahead and choose the negative here. So that way we're calculating out upward flux. When I distribute that, right, we'll have positive 1, 1, 1. All right. So let's go ahead and evaluate out our dot product. We have x times 1, we have y times 1, and we have z times 1, which again, our z was 1 minus x minus y. Notice that my bold ds went to dA. We're now in the xy plane. So we've taken this thing, the surface that was hovering in space, and now that we're started to evaluate this and we've gotten rid of our ds, right? We swap this out for dA, and we plug in the correct normal vector and all that sort of stuff. But we need to smush this into the xy plane because there's only going to be x's and y's left at this point. So if I take this and I smush it into the xy plane, this kind of oblong circle, this ellipse that was hovering in space, now gets smushed down. And again, it lies inside of this cylinder of x squared plus y squared equals 1. But now it's in the xy plane where z is equal to 0. Right? And so this R, this region here, is inside of a circle of radius 1. So this should be, this point, these should be R's, not S's. Positive x, positive y, those can nicely simplify a little bit. And now we have a double integral of 1 dA. Not 1 ds, anything like that. It's 1 dA, which means that we are interested in the area, right? Because the double integral of 1 dA is area in the xy plane of the region that we're integrating over. And so this is going to be, well, just pi r squared, which happens to be pi. So this just means, right, when we've talked about this flux, this means that we calculated out upward flux. If we were to draw this vector field, right, our picture didn't include that vector field, but there would be more vectors kind of pushing particles upward through this than there would be vectors pushing particles downward through the surface. So again, flux is how we're pushing particles across the surface. And so there's more pushing up than there is pushing down. The upward flux is positive. All right. Any questions on this one? All right. Just as an FYI, right, unless otherwise specified, assume that your closed surfaces are always oriented positively. That's kind of the default here. Oh, something in the Q&A. So for upward force, the z should be positive. So the sign of x and y doesn't matter. Correct. That's a true statement. If it says we're interested in the upward flux, then really you're interested in the z component there, not so much the x's or the y's. All right, let me just peek here. Yeah, so we'll do this one. This is kind of our last one here. evaluate out f dot ds, bold S, bold F. We go on to specify what our vector field is. So again, this is a flux calculation. This is a surface integral with a vector field, not a surface integral with a scalar function. Like it's not just y there or z squared or something like that, right? We actually have a vector field. If you wanted to, you could even spend a line to rewrite this. Y, x, z dot ds. And again, this is a bold S. The boundary of the solid region E enclosed by the paraboloid and the plane. So S is really made up of two pieces, right? So if we were to talk about the solid region, we have this paraboloid, which would normally go on forever, and we have this plane. And so the two of them kind of completely enclose this region here. And so if you want the surface integral over the entire boundary of this 3D region, you want it across the top piece, but you also want it across this plane. So again, maybe I can do some shading to kind of make this a little bit clearer. To enclose the 3D region, you need to have both this paraboloid and you need to have this plane. But again, these things are kind of bounding each other. They're not going on forever, right? So the plane has the equation z equals 0, but again, it doesn't go on forever. It's only a piece of it. And this paraboloid has the equation z equals 1 minus x squared minus y squared. But again, it doesn't go on forever either. It stops kind of once you hit this plane. So in order to evaluate this, we're going to kind of evaluate this into two pieces, right? So this is maybe our overall S. I'm going to evaluate this on my kind of two pieces, S1 and S2, and then we're going to have to add those together. So kind of very similarly to what we did with our sphere, right, where we evaluate out the surface integral in the top half and then the bottom half, and then we added those together. Likewise, same sort of deal here. Now I think S2 is very fast. So let's go ahead and first evaluate out our integral on S2. Getting ahead of myself a little bit here. So on S2, the surface equation is z equals 0. So notice for my vector field, I substituted everywhere I saw a z, I put 0. That's very similar to our last one, where we had a more difficult equation. But again, everywhere I saw a z, I plugged in the surface equation. Now I need to find my normal vector here. And so I need, in this case, a partial derivative with respect to x, a partial derivative with respect to y, and then -1. My surface equation for S2 is just 0, right? It could have any number of x's and y's on the other side. And in fact, when I look at the other one, it does have x's and y's on the other side. But for this one right here, it's just the nice 0. And so when I take a partial derivative with respect to x, or when I take a partial derivative with respect to y, well, I get 0. Now, in this case, we have not specified, right, an orientation for our surface. So we go back to our remark. Unless otherwise specified, assume closed surfaces are always oriented positively. That is an outward orientation. So that is, if I was to draw normal vectors here along my bottom piece, right, this z equals 0, they'd be oriented downward. That's the same thing as outward in this case. And for my paraboloid, they'd be pretty much all pointing upward. Maybe along the edge here, they're only slightly upward, sort of deal. But this would be for our normal vectors pointing outward. And so let me go ahead and do the same sort of picture here. Oops. There we go. Some outward pointing normal vectors. So again, along S2, if I want these pointing outward, that means that's equivalent to pointing downward. So when I look at this for my normal vector, I have 0, 0, -1. Am I happy with that? Yeah, absolutely, right? I want it pointing downward. And so I'm going to choose the positive here. Notice that in either case, when you evaluate out this dot product, you're going to be getting 0. Where now, if we took this region and smushed it down into the xy plane, well, but the integral of 0 is just 0. So like I said, this one's quite easy. So I see that we are out of time. So this is kind of where I'll stop here. But let me just write at least to get you guys started on this. Instead of z in this case, we're going to be writing our 1 minus x squared minus y squared. Partial derivative with respect to x, partial derivative with respect to y, -1. We have to decide if we're happy with that or not. And then that's what you're going to be evaluating out for your second surface integral. All right, so like I said, didn't have enough time to cover all my problems by any means. I'll go ahead and finish these up. There's enough here that I'll probably just make a video for the problems that I didn't finish up. So expect that on D2L